Hey everybody, this is Mr. Schaefer, and I'm here to help you with some AP exam review for calculus. Specifically, I'd like to talk to you about the syntax and proper usage of L'Hopital's rule as you might see it within an FRQ. So I have for you a list of things to think about when you think that you're going to use L'Hopital's rule. Remember to make sure that you show that the necessary conditions have been met. And with L'Hopital's, that means that the limit overall takes on that indeterminate form. For example, infinity over infinity, or 0 over 0. Those are called indeterminate. We don't just want to simply start taking the derivative of the numerator and the denominator without stating why we're doing so. And one of the ways that we can kind of help that, or help not do that, is by using proper limit notation. So this answer to the question why will come from using proper limit notation throughout your problem. And be very careful to never state some kind of limit sentence that is not true. For example, a limit cannot equal an indeterminate form. Mathematically, that statement just doesn't really make much sense. It's not true. It can't happen. We wouldn't really want to say that a limit is equal to infinity. It might be helpful to think of that, but we can't ever reach infinity or negative infinity. So to say that a limit is approaching infinity makes sense, but we don't want to ever say that a limit equals infinity. Likewise, we don't want to say that a limit is equal to 0 over 0, because that can't really happen. A limit cannot equal something that does not exist. So to that end, I have for you an example from an FRQ that I thought we could look at and kind of make sense of what's required of students when they use L'Hopital's rule. You have a differential equation, dy dx, and it says that y equals f of x is the particular solution to that differential equation with the initial condition f of 0 equals negative 1. And the only problem I want to do is this first one that says find the limit as x approaches 0 of this expression, and then show work. Well, I'm thinking sort of quickly that this may be a L'Hopital's rule problem just based on what I'm going to be plugging in. I see a sine of 0 happening in the denominator, and then f of 0 is negative 1. I'm going to add 1 to that and get a 0. So with a little bit of mental math, I can see right away that this is going to be a candidate for using L'Hopital's rule. But before we just dive into that rule, let's first, again, show why we're thinking that way and kind of explain with notation what we're looking to do. So I'm going to write down the limit as x approaches 0 of the numerator, f of x plus 1. Analyze that separately. By direct substitution, I can get that to be equal to f of 0 plus 1, and f of 0 is negative 1. Negative 1 plus 1 is 0. In a completely separate line of work, we're going to write down the limit as x approaches 0 of the denominator, which is sine of x. Once again, that is going to be equal to sine of 0, which is just 0. Two separate lines, both with limit notation present. That has to be the case, here and here. Include your limit notation when using L'Hopital's. Notice that nowhere in my work so far did I say that a limit was ever equal to an indeterminate form. So be careful that you always avoid writing any kind of mathematical statement that is not true, especially when it comes to limits. But the problem still wants me to find the limit. So I'm going to use L'Hopital's rule. State the name of your theorem. You can say by L'Hopital's rule. And then, with proper limit notation, don't forget, now I can take the derivative of the top, the numerator, and the derivative of the denominator. F of x plus 1 has a derivative of f prime. Sine of x has a derivative of cosine. And then if I plug in 0 to these values, I can use direct substitution to compute the limit. Let's see if we actually get a value, or if we get another indeterminate form, in which case we'd have to use L'Hopital's rule another time. F prime is 0. Well, f prime is not stated anywhere, but dy dx is, and that's the same thing as f prime. The definition of f prime, or dy dx, is y squared, parentheses, 2x plus 2. Well, we want to compute that at 0. So, in other words, what is dy dx when x equals 0? But when x equals 0, I know that y is -1 from this initial condition. So now I have the two values, and I can plug them in. -1 squared for y, or -1 for y, and then squared, 2x plus 2, 2 times 0 plus 2. This is going to become a value of 1 times 2, or simply 2. Cosine of 0 is 1, and my limit will have a value of 2. But again, I want to draw your attention to the use of proper limit notation throughout this problem. Here's the rubric. Notice that the student would earn a point for the proper application of L'Hopital's rule, which is done down here using limit notation, and then the answer point of 2. However, the student would not earn a point for proper usage of L'Hopital's rule if this initial syntax was missing. Make sure you show that the limit of the numerator is some value, and the limit of the denominator is another value, and that the quotient of those two values is, or somehow represents, an indeterminate form. Now, on an unrelated topic, I'd like to present to you just a quick reminder on how limits of compositions work, because L'Hopital's rule is actually a limit problem, or it's actually a rule that helps us find limits. There's just one more kind of question that we should know how to do. Here's a multiple choice question that involves the limit of a composition. Here's a graph of f. Find the value of the limit as x approaches 0 of f of 1 minus x squared. So for this problem, I tend to take this outside part of the function and just kind of bounce it out over here to the outside of the limit. So what that means is, what I'm really evaluating here is f of some limit, the limit as x approaches 0 of that inside function, 1 minus x squared. But I've got to be kind of careful with what I evaluate here. Let's look at the inside function, the limit as x goes to 0 of 1 minus x squared. Here a picture will come in handy. So 1 minus x squared is a parabola that opens down that has a vertex at 0, 1. Think about what happens as you approach 0. Approach 0 from the left and from the right. Notice that you're going to have a limit of 1. But you've got to notice that the limit is always approaching that 1 from below. So you never really get to that 1 because limits are never about what's happening at a certain point. They're always about what's happening as you approach, as you get closer and closer to that given point. So this limit in a standalone problem would have an answer of 1, but this is not a standalone problem. It's a limit of a composition. So f of 1 by itself is not exactly what I'm going to try to compute here, because I'm always below that output or that intended height of 1. I've got to make sure that I think about plugging in numbers that are also below. So I'm going to put a little minus sign in there to remind myself to always look lower than 1 as I approach 1 on the input. So what is f of 1 using values that are just always lower or less than 1? So here's my picture of f. As I approach 1, which would be right about here, I just want to approach 1 from the lower side of it, from the left side of it in this case. And notice we're going to actually approach an output of 3. It doesn't matter that f of 1 is down here at 2, because limits aren't about what's happening at the point. They're all about what's happening as you approach the point. So the solution to this problem would be choice B. So a quick reminder on how limits of compositions work. They're tricky, so be careful and always work your way through them conceptually, not too quickly so that you don't miss certain key details and get tricked. Thanks for watching. I hope that was helpful for you today.